When you want to launch any payload into space, the formula you use to calculate how much fuel you will need is called the rocket equation. According to this equation, 90% of the weight of a rocket going to orbit is propellant weight. The remaining 10% of the weight is structure, engines, and payload. So, given the current state of the art, the payload accounts for only about 1 or 2% of the weight of an ideal rocket at launch. If you want to load more payload, you need more fuel. To carry this additional fuel into space, you need even more fuel. It can become an endless loop, and can give you a headache. When you want to launch a satellite to low Earth orbit, the rocket equation can be relatively easily calculated. However, things get more complicated if your satellite is heavier, or if you want to send it further away, like to Mars or Jupiter. The amount of fuel you need to carry increases dramatically that there might not even be enough margin for your satellite. The solution to break free from this never-ending fuel hunger lies in electric propulsion systems. Welcome to the spaceship Earth. In this episode, we will talk about electric propulsion systems, their types, and characteristics. Electric propulsion is a class of space technology aiming to propel a spacecraft to higher speeds with less fuel. The main principle is to accelerate the exhaust gas by using electric energy, and thus increase the spacecraft's velocity. If we look at the history of this new and groundbreaking technology, the idea of electric propulsion for spacecraft was introduced in 1911 by Konstantin Tsiolkovsky, considered the father of rocketry. The first practical research began in the 1960s, after the technology became feasible. NASA conducted ion engine tests using mercury and cesium as propellants, while Soviet Russia successfully used Hall effect thrusters for precise positioning of communication satellites. After continuous researches and applications, electric propulsion systems have now become actively used in many spacecraft. When we look at electric propulsion systems, we can see that they are not used in rockets during launch from Earth to space. The reason is that they cannot generate enough power to escape from Earth's gravity well. When an electric propulsion system operates at full power, the force it produces is equivalent to the force exerted by a sheet of paper you hold in your hand. With this amount of force, it's not even possible to move a rocket from the launch pad. The real power and high efficiency of these electric motors come not from the amount of thrust it produced, but from their ability to sustain this thrust for long periods. A typical solid-fueled rocket burns its fuel and stops after about 100 seconds. A liquid-fueled rocket, depending on the amount of fuel it carries, can operate for approximately 480 to 540 seconds. About 8 to 9 minutes. However, an electric propulsion engine can operate for millions of seconds, equivalent to months. For instance, an ion engine tested by NASA ran continuously for 5 years, using 700 kilograms or 1,500 pounds of propellant, setting a record in this field. This ability allows spacecrafts to reach very high speeds in the frictionless vacuum of space. By using electric propulsion systems, it is possible to achieve incredible speeds like 144,000 kilometers or 89,000 miles per hour for a spacecraft. Achieving such a speed with traditional solid or liquid-fueled rockets is extremely difficult. This speed allows for deep space missions without waiting for home and transfer windows, which occur every 26 months for Earth-Mars missions, or much longer for deep space missions. Looking at electric propulsion systems, we can classify them into 3 main groups based on how they produce thrust: electrothermal, electrostatic, and electromagnetic. Among these 3 classes, the most preferred type is the electrostatic propulsion method. In this video, we will talk about ion and Hall effect thrusters that use this method. Ion engines operate based on the principle of ionizing atoms, and then accelerating them to high speeds with the help of a magnetic field, and obtaining thrust. Typically, noble gases like neon, krypton, or xenon with high atomic numbers are used as propellants. Among these gases, xenon provides the highest thrust per atom and is, therefore, the most preferred propellant. Ion engines create thrust by expelling ionized atoms at a speed of 160,000 km or 99,000 miles per hour from a pot-sized thruster. This acceleration is very slow, depending on the size of the engine. It may take 3 to 4 days to increase the speed of a satellite to 100 km or 62 miles per hour. However, as mentioned before, ion engines can operate for very long durations. After running for weeks or months, they can thrust the attached satellite to speeds as high as tens of thousands of kilometers, miles per hour. As a notable example of the capacity of ion engines, we can mention the Dawn spacecraft, which is the only spacecraft to orbit 2 celestial bodies beyond Earth. The Dawn spacecraft visited the protoplanet, or dwarf planet Ceres and Vesta, in the asteroid belt between Mars and Jupiter, using its ion engines. After entering the orbits of both objects, Conducting the necessary scientific studies, it then proceeded to its next destination. Another commonly used type of electric propulsion system is Hall effect thrusters. The Hall effect engine, or simply Hall engine, similar to ion engines, works based on ionizing atoms to very high speeds. However, it uses a different method to accelerate the generated ionized plasma. The ionized plasma is created vertically with an electric field within a magnetic field and then accelerated at high speeds. Hall engines are not as efficient as ion engines, but they are less complex, and have higher power-to-weight ratios, making them more preferred in practical applications. Another reason for the preference of these engines is their advantage in scaling. They can be used to guide very small satellites, as small as fits on a nanosatellites, or even larger models, nearly half a meter, to move space stations. Similarly, in the Starlink satellite constellation, the crafts are equipped with Hall engines using krypton gas. The reason for using krypton gas, instead of the more efficient xenon gas as fuel, is the lower cost of krypton. As a final example, the Gateway Station, which NASA is preparing to establish in lunar orbit, will use advanced and enlarged Hall effect engines to control its maneuvers in orbit. These Hall engines, located in the station's service module, successfully completed their propulsion tests and are being prepared to be attached to the module. NASA is also working on X-3 thrusters, an advanced version of Hall engines, to be used in large space probes and even crewed spacecrafts to propel them into space within the next 10 years. In the endless expanse of space beyond Earth and Mars, we need to find a new, and fast system apart from the solid and liquid-fueled rockets to reach even further. In this quest, electric propulsion systems emerge as the most suitable candidate for the next generation spacecrafts, thanks to their high efficiency and the high speeds they can achieve. Thank you for following the Spaceship Earth. If you found our video helpful, please give it a thumbs up. Subscribe to our channel to stay updated on space and space technology news.